A minus 90 to 92.
Oh, okay.
Not including 92. Okay. So there's a question. And this is one of those situations, again, where if I don't get this question, I get a little concerned. Or I'm just optimistic that you guys figured it out. When you solve, so Ryan, what is your question?
The question is x plus y plus z equals 0.
Section.
At 10-2. Negative x plus 2y plus 5z equals 6. And 3x minus y equals 12. And I'm pretty sure it's supposed to be infinite solutions.
Pretty sure, all right.
Pretty sure.
So,
Every different way I've done it, I came out with 0 equals 0 somewhere. And
there's two ways to do this problem, considering that it's, and what's really kind of nice about this, if you allow it to be nice.
you don't have a z's
Yeah, one
already.
z's already gone.
Yeah.
So you can look at this two ways. You can either do what? I mean, normally we try to kill the same letter twice. Well, there's already a letter that it's just it's DOA, right? This letter, and Z is dead already in the third one. So between 1 and 2, I can kill Z again. And then I have two equations with just X and Y. Beautiful, right? Or you can solve this one for Y and plug it in there, and then you'll have two equations with just X and Z. I mean, either way you want to do it. You guys see, you got a couple options here. So which way you want to do it?
However, I did it
First
both
way.
ways.
All right. So if we take 1 and 2, what do I have to do to kill Z?
One by negative 1.
All right, beautiful. So if I take 1 multiplied by negative 5, what do I get?
Negative 5x. Minus 1.
All right, that's easy enough. And number 2, we leave that dude alone. He's already got positive 5Z there.
Negative 6x.
Yeah, so negative 6X
3. Negative 5.
times 3Y equals 0. And so that's my fourth equation.
Equals 6. It would equal 6.
Oh, 6 here, yeah.
Mhm.
Thanks. So then that's my fourth equation. And then you can see what I could do there. Just make it a little bit better.
Take a 3 out.
Yeah, divide by like negative 3, let's say. So I get 2x plus y equals negative 2. Alright, we'll stop there. Is that cool?
Yeah.
So anytime you can divide, you go ahead and do it. If you don't notice, it's going to help you out later. And number 3 already says 3x minus y equals 12.
Taking it 4.
Yeah, so they're already set up beautifully for this. So I don't think it's going to work out the way you thought. Maybe, let's see.
Well, when I did the watch it video, it was infinite solution.
Oh, I see, alright. 5x equals 10, x equals 2.
Which is not what I got ever.
Uh-oh. So this is not going to do...
Okay, then I'll give you the other one. I got a different one then.
Oh, let me make sure. This is, again, if you missed the last time, this is a review. This should be a problem you could totally do before this class even started. So x is 2, so then y would be, if you put a 2 in there,
Negative 6.
negative 6, so y is negative 6. Get in there. So then z, x plus y plus z is supposed to be 0. X plus y is negative 4.
So it's 4.
So z's got to be 4. Alright, I like it. So geometrically, what's going on?
One solution.
They're all meeting at one point.
What's they?
The 3 planes.
Good. These are 3 planes, and they all meet at a point somewhere. There's a lot of ways they could not meet at a point. Okay.
You can do it.
Exciting stuff. So let me cut to the chase. If you solve a system of equations and you get to the point, let's say we got to this point here, when we solve this, and we got this guy again. Let's say number 4, we got 2x plus y equals negative 2. So in the process of solving, we get to this point, and then when we did this, we got 0 equals 0. Let's just pretend that for a second, because that's what I was hoping would happen here.
But it didn't.
So we have this equation, and then we killed some to make this equation, and then that one together with the other one somehow just canceled out. So it used to be okay. It used to be okay to just stop there and say, infinite number of solutions, right? In reality, you want to be a little more precise about it, because remember what we said the other day. If I had, this was one plane, and the ceiling was another plane, and a third plane was coming in like this, sort of like a Rolodex, if you remember those back in the day. You know, sort of like 8-track tape, the same kind of thing.
Is there any way of actually checking these with 3 variables on your calculator?
We're going to find that out today. Yeah. If that was the case, then the answer would be that line, that's the crease there, right? The answer would be the line. So it would not be wrong to say there's an infinite number of solutions, but you could be more precise. You would say all the solutions lie on that line. And in fact, you can find an equation for that line. Craziness, right? So what the hell else can we do here?
Find the equation for the line.
So it looks to me like z is by itself, right?
Mm-hmm.
Z is a function of x and y. Is that cool? And y is a function of x. So go with me here now. Are you ready? So whenever this kind of thing happens, this is what you got to do next. And they have some examples in the book like this. If I solve this for y, if I take 2 and solve for y, I get this here, right? So this should look a little familiar. If I say let x equal t, what's y equal?
Negative 2t.
Negative 2t minus 2. And then what's z equal? What's x?
Negative y minus t.
What's that? Yeah, x is t.
Oh.
And y is this business. Let me stop right there for a second. So we define this because x is kind of like controlling y, and then together they're controlling z.
Do we always change x to t in these cases, or
No.
does it
No.
matter?
To be completely honest, it actually doesn't matter which one you call what. Because you can always plug them back into each other. But I always like to try to get one of these two would be t, because then together they're controlling z, right? And we think of parameters as being behind the scenes controllers of something else, right? But it doesn't matter what you call t, because they all are related to each other. You can still do what we're doing right now. So the minute I call x t, that means y is negative 2t minus 2. And now that I know x and y, I can plug them in here and figure out what z is in terms of t. So what's z here?
Negative 2 plus 2t.
So t plus 2. Kick ass. So how many true variables controls this thing? Do you guys see what I mean when I say that? There are like 4 variables up there, but 3 of them are controlled by 1. So there's really just one variable that's allowed to do whatever the hell it wants to do. Do you guys see what I'm saying?
It's t.
And it's t. Good. So we'd say this is a one-dimensional answer. This would be a line. This is the situation. If it ended up here, what that means is 2 of the planes met, and then a third plane in and came at the same line that the other 2 met. So believe it or not, these here describe a line in 3-dimensional space. Absorb that for a second. Start sunshine.
You made y could have been t, right?
Sure, y could have been t. Because then I could have solved this for x.
Okay.
But you can maybe see why I let x be t, so I don't have that fractions coming into play, right? So you have complete flexibility as to how you define it. But no matter how you define it, your t might be different values, but it's going to come out with the same x, y, z values that my t would. Right? You can define it differently, but it's still going to describe the same line. So there could be a situation where I get 2 rows of zeros. 0 equals 0 equals 0. Then the answer would be this plane. And how many dimensions does a plane represent?
1.
So a line is 1 dimension.
Oh gosh.
A plane is
A lot.
2 dimensions. No, it's not a lot, just 2. And then, of course, a cube kind of thing, a volume would be 3 dimensions, right? And then you have a hypercube, 4 dimensions. Ooh, worship. Let's come back to... So one variable, one parameter controlling it means it's a line. If I had a situation where I had to use t and s, oh yes, then the answer would be a plane. So So for example, real quick. So again, this is not horrific. We really are just making x, replacing it with t. And once we do that, we can get y in terms of t, which allows us to kind of simplify this down quite a bit. Everything's controlled by a single variable t, which makes it easier to think of geometrically. There's really only one true variable. There's one dimension of movement, which means it's a line. If there were two dimensions of movement, s and t, that would be a plane. So the easiest way, let me see if you guys can get this. All right, here we go. Right. So let me make up a little thing. You shouldn't have to do any work to figure this out. Become a y. Can you guys see anything about this that makes it almost too easy?
Yeah.
Simplify it all down to this.
When you add
They're all the
together
same.
Yeah, they're all the
the first and second line, they equal.
Set.
Well, we,
The opposite.
Yeah, so all three of them will cancel out. This one is twice that one.
And that one is.
So I could negative 2 times this plus this would make 0 equals 0. So this would become 0 equals 0. Is that cool?
Yeah.
If I did negative 3, or just 3 times this plus this, that would be 0 equals 0.
Well, is that your answer then?
No, the answer is going to be something like that. So over here, I had a relationship between x and y. That's why I was allowed to let x equals t and then y is in terms of that. Do I have anything like that here? What's the only thing I have?
That.
Just that.
This. So if I let x be little x dude, I have to, what could y and z be? Are they related to each other? If y is 3, does z have to be something?
Yes. No.
No, right? Y and z could be anything they want to be.
Okay.
And then x would have to be whatever makes it come out before. Do you guys see that? Over here, why did I not have that much freedom?
Because there's only two
If x is 2, then y must be what it has to be to make it negative 2. It's got the extra requirement. Do we have that here? No, it canceled. So I have more flexibility, more freedom to move. That's why I come out with 2 parameters here. If I let y equal t, and I let z equal s, what do I get? I get x equals negative 2y minus z plus 4. So I get x equals,
Negative 2t minus s.
that's the answer. And that is a plane. It's got 2 parameters, 2 dimensions of movement. It's a plane. You're not going to see this a lot, but I just want to show you one example of this. You're going to see that in this homework, where you have to define, let one letter be t, and then the rest of them are just based off of that. Yeah.
so on the homework, would you care if it's just like showing that x is the solution of that, or do we like need to replace the y and z? Do we need to do that?
Yes, you do. Because most of the time, you're not going to get this a lot. This is almost too simple. In fact, I'm kind of like what you're thinking. Why the hell would you even do that? And to be completely honest, there still is another reason for that, but that's later. But you're going to get this, and I could never have written this unless I had made x and y both based on t. I could never have made this simplified like this, unless I make them both based on t.
Well, I was thinking that if you were to want to try and sort of make a Cartesian type deal, you just solve the same thing but for y and then you sort of those together? Or have you seen that? Does that make any sense at all?
Sort of. But you're trying to, again, this is like 3-dimensional, and
Yeah, I realize.
y equals x or x equals a function of y really doesn't matter. It's completely arbitrary that we chose y to be the dude we solve for most of the time. Right? Yeah. Yeah.
So is this just one method of doing it, or like is this what you expect?
This is basically the accepted way of doing this. Yeah. I mean, this is one way you could do it. But every problem, there's one way you could that's been accepted, and there's a million other ways you could do it. Yeah, so this is the way to do it, especially for this kind of problem here. I mean, you can't get there unless you do this. Because then x and y, you can combine them. They suddenly have like terms in them, right? They're both based on t. So then z, I can make it a nice condensed form. And then everybody's controlled by one amount, one variable. Right, in this case, t. Okay, so that's the one extra little bit of added weirdness to these relatively simple problems. right? That's the only thing. And whenever you get this, then that's the only time you got to worry about this. Okay, good. Good.
Good.
Yes.
This is on 10.1. The 21 through 48, how it says express them in order of pair form, given an example 6. Now I'm trying to look at example 6, I'm not quite.
Wait, let me catch up to you here. Which one are we looking at?
21 through 48. Anyone that doesn't know.
Okay.
But how it talks about expressing them in order of pair form as an example 6. Now looking at it, I'm like, I don't.
Oh, okay. So I can take this one thing further. This guy. And what would it look like? X, Y, Z. What would I put there? T.
Negative 2, T minus 2. And then T plus 2.
There you go.
Now, but when you're
So
doing
that would be ordered pair form.
But
Ordered,
when
in
you-
this case, ordered triplet.
when you're doing these though, do you just start from the very beginning and just say, hey, okay, X equals T, for example, and then you just input T for all of
Oh,
this?
hell no.
Or do you wait until you pretty much
Because you
solved
don't
it?
know until the end if X can have an infinite number of answers. The only reason I'm allowed to say this is because this tells me I have an infinite number of solutions.
So it's only when they're infinite.
Exactly. Otherwise, I can't let X be T. I've got to figure out, is it 2? Is it negative 7? Right? So I have to know first that there's an infinite number of solutions before I can just assign the letter T to it. Does that make sense?
Yeah.
Okay, good. Yes, ma'am.
Can you do number 59 on A4?
No, that's the only one. No, let me see. 84, 59. Oh, hey, all right. That looks familiar. So let me give you something to get started on. And that's another one that if I don't hear a question about it, I'm a little worried about how to interpret that.
What page is this?
This is the one you were talking about earlier.
Oh, yay.
This is page 570, section 10.1.
8-4.
So 8. What did I say? Yeah, I'm still stuck with the other 8-4. Sorry. All right. So here's what they give you. So let me give you an idea of how to attack this problem, because it sounds really kind of freakadelic. And this is really kind of the idea of the spirograph. If you think about it, these things are rolling inside of something else. So when you put your pen in, you define what the point P is, and then you trace it out for spirograph. If you have no idea what spirograph is, just look at the picture. Let's see, theta. So we got this dude here. We got theta here. What are they trying to say? Oh, that's a radius B. And they got this point P. So as this thing rolls around inside, it's like there's a pin right here on the P. So as it rolls, I'm kind of collecting all the places where that point P goes. So you're going to get this really neat little shape to it. And if you think about it, if you put your calculator in parametric equation mode and put in there what the answer is, give yourself your own A and B for the answer, you'll get the shape. You'll get what it looks like, right? Okay, maybe. So here's what you got to do. For this point P, what point is that? I love that question. I don't know what the hell you want to do. So here's A. This is radius A. And this little dude is radius B. But all I really want you to say right now is this point is the point X, Y. And so you're trying to figure out equations for what X and Y are. So look at what X is made of. Let me kind of blow this up a little bit. So here's theta. I don't want to put that in there yet. Here is A. Here's X. So really X is made up of this piece plus this piece. So it's made up of this here piece from this right triangle here, plus this extra little piece here. Alright, so if you've got the picture in front of you, it's a little bit easier to see it in there than on my rapidly becoming very populated with crap here. Just to give you a little hint, now this is not that bad. This one you should be able to get. How long is this here? This is where things kind of start coming together. So I was lying a little bit on. You start to pick up some of the answer right away. So how long is this whole thing? What's the radius of the big circle?
That's
One.
Hey! And what's the radius of the small circle? B. All right, good. So how long is this? It's not A, it's A minus B. Now look at the answer. There's some A minus B's in there. You go, oh shit, that's crazy. I'm on the right track. Why did I even know this? Because I know part of X is this side of this triangle here. So this is going to be all the way out with the A minus B. This is A minus B. That's how long this hypotenuse is. And I know it's a right triangle because I drew that down. Oh, yeah, right triangles. Yes, cool. No law of anything. Just freaking right triangles. So how long is this piece here? What do I use? Hypotenuse, the x side. What trig function?
cosine.
Cosine, yeah. So cosine theta would be cool. So x is, I'm sorry, let me be careful. Let me be careful. So this whole thing is x, right? This whole thing is our x. So we'll call this little piece here, we'll call this x1. Don't get too excited, right? It won't be our total answer for x. But what is x1? What's that little piece there? And then I got to figure out what that is so I can add that little piece to it.
X2.
x2, it's crazy, right? Second?
A minus x1 equals a minus b times.
Yeah. A minus b times cosine theta. So if you look at the answer, that's the very first part of the damn thing, right? A minus b times cosine theta. So the rest of that must be this weirdness. The length of that little dude there. And my hint for you is there's a little tiny right triangle there. A little tiny right triangle there. That's maybe not the only way you can get that distance. But that's the most immediate, direct way you could do it, right? Whether this hypotenuse is B, this side is the one you want. If you can figure out what that angle is, you keep going. That's all I'm going to give you. So I've given you a little bit to get started. And you do the same thing with y. You say, what makes y? Is it the subtraction? So look, y looks to be not quite this whole thing. It's this whole thing minus a little bit, right? So that's why in y, you see how there's a negative sign in the y piece? Okay, that jives with what we just said. Cool. All right, so it all boils down. This was relatively easy. You guys might say, it wasn't easy. Relatively easy. That was relatively easy. Because the hard part is all about this little teeny freaking little triangle there. This little triangle, that's B. I don't know this angle yet. But this is going to be the x piece that I want, the x2. And this much is going to be somehow related to y. Actually, I'm going to want to use a different triangle for that guy, but I'll let you figure that out. That one's going to be exciting. If that's the only problem you're having trouble with in that section, you're doing fine. Right, that problem is not supposed to be easy. Yeah?
51, same section.
Does anybody have any questions on that before? I'm sure everybody does, but I just want to get you started as to how to approach this. And you got to get to the point where you're just okay with just playing around with shit. Zoom in on some of this so you can focus on what triangles you're using. Right? So 51. In that same section, 8.4. So it says, part A says express that in parametric form. And then part B says, using graphing device to graph this. Okay. And they give you the approach to this. They give you on page 568. They tell you how to do polar equations in parametric form. Page 568. So they tell you if you let x equal, let me say this. So if r is a function of theta, and r definitely is a function of theta up there, right? I can see what f is. There it is. Cool. Then you let x be f of t cosine t, and you let y be f of t sine t. just make that happen. All right, so for example, what's f of t then?
4
Yes.
cosine t.
4 over 2 minus cosine t. Is that cool? That's f of t. Because that's f of theta there. Just put a t in for theta. Times cosine t. That's what x is. And then y, you do the same thing. So that problem sounds like, oh my God. But you got to go back and say, I mean, this is a direct process they give you. And if you think about it, if I know what the radius is, how do I get x? If I know r, how do I get x from it? X is r. No? What's the basic definition of x?
R cosine theta.
Thank you. Okay. And see what they did? They took r times cosine, not they call it t, not theta, but who cares? It's because it's a parametric, right? So it's exactly, and then how do you get y? Is r times sine of the angle, and we're calling the angle t because it's a parameter. Maybe. So that process almost seems too straightforward to trust. You just do what we always do. Just whatever the expression is for r, we treat it like r. Why can we do that? Because it is r. R is this. So how do you get the x piece? R cosine. How do you get the y piece? R sine.
Yeah, but with the function of t, wouldn't it still be, for the sine of t, it'd still be the inside portion would be 4 over 2 minus cosine t?
What's f of theta? In this problem, what's f of theta?
4 over.
It's this. So what's f of t? Put a t there. And that's what they need there and there. So both of those are going to be the same. Cool. Yes, ma'am?
Can we go over 10-1, number 71?
Okay. Oh, yeah. So the trick with this one is to realize you can use more than one variable in this thing to make it very straightforward at first to set it up. If you didn't do that for yourself, it'd be really freaky trying to make the little chart for the distance, rate, and time. So what I'm trying to say is, what do I know here? John and Mary leave the house at the same time. Look at that amazing creativity with names. This is section 10.1. Right, this one about John and Mary. Make sure we're talking about the right one. Number 71. Distance is rate times time. So you got John, you got Mary. It's actually my name and my sister's name. That's are my creative parents. John drives at 60 miles an hour. Beautiful. Mary drives at 40 miles an hour. Kick ass. All right. So 60 miles an hour, 40 miles an hour. It's actually the reverse from my sister. John travels 35 miles farther than Mary. So in terms of distance, who am I going to call X for their distance? Mary. Because John did something added on to that, right? So if Mary went X, John went how far?
X plus.
Yeah? 35, right? Alright, cool. And then Mary's trip takes 15, now here's where they get evil. 15 minutes, not 15 hours, 15 minutes longer. Yeah, so 1/4 of an hour. Right? So who's going to be just Y then for the time?
John.
Yeah, John's going to be time, it's going to be T, and then Mary takes 1/4 of an hour longer. So allowing yourself to use multiple variables made that a lot easier to set up. And now you just write the equations you get from both. Right? What equation do you get from the first one?
X plus 35 equals 60.
Equals
61.
60y. Rate times time equals distance. Yeah. Do the same thing for the second one. Eliminate however you want to. Substitution, elimination, whatever you want to do. Right? Comes back in.
That was funny. Was that? Did you say that was funny because that's your name and your sister?
Yes, that's right.
Okay.
That's what I said. John and Mary. Oh boy. What are we gonna do?
So Jeffrey's your middle name?
Yes, Jeff's my middle name. Thankfully, my last name is not Waterson. That might have done me good. I would have had more practice saying that. Okay. Yes, one last thing.
Okay, can we also go over number 74 in this one?
In 10.1?
Yeah.
Oh, so this is the one that gives you this freakiness here. And they want you to find this area. So, to find the area of a triangle, what do you need?
Base and height.
Yeah, so they give you what these equations are. Doesn't really matter. I'm not going to say that much about this anyway. So the height would be how related to the equations that they give you.
When you find your x and y,
Yeah, if I find the intersection, it's going to be the
that'd be your center point.
y piece of that, right?
Yeah.
Cool. And then, of course, the base, I just have to see
Set each one equal to
how
0.
far apart those are, right? All right, so it's not bad. It's not bad. It looks like it's going to be horrendous, but it's not bad. Just find the base. That's just the distance between those 2 points. So find the roots of that, the roots for each. And then the height is just going to be the y piece of where they meet, right?
So is it just finding x and y, or?
Pretty much, but for two different situations. So one part is going to be here. This is going to be my height. And the other part are going to be these two. The x's of those two take the difference. It's going to be my base, how long my base is. Right? If I knew that this was 0.7 and this was 4.2, well, how long is that? 4.2 minus 0.7. So just find the x pieces for those. The difference is the base. Find the y piece for where they meet. That's the height. So really, the place to start is when they ask you for the area of a triangle, you say, okay, I need the base and the height. How do I get that from what they tell me? That gets you started. Right? Don't look at it and go, how do they want me to do the area in this? No. I know how to get the area of a triangle.
Yeah.
Let me force that to tell me what I need.
How are you getting x from it? Are you actually putting them in a system of equations?
No. Just how do you get the x-intercept for this? How do you get the x-intercept?
Oh.
Yeah, just the x-intercepts of those. Yeah. Okay, let's get back into... We're going to get into section 10.3 now. And it looks like a decent number of you guys have done matrices before. We're, of course, going to go a little bit deeper into the idea of matrices. And to give you a little bit of a preview, it's sort of like the same idea with synthetic division. It wants to get the variables out of the way because the most important things are the numbers. So I'm going to do 2 by 2. Let's show you. I know there's well, let me just put it there. Let's see. I don't know, Jeff. What do you want to say? Sure. That's cool. All right. Let's all see if Jeff did that quickly. So if you were here, I call this a 2 by 2, even though some of you might argue that it's actually a 2 rows by 3 column. It's 2 by 2 because there's 2 equations, 2 unknowns. And the real matrix at the heart of this is this guy, the coefficients of this guy. Bless you. So whoever's here the other day, or if you just know, how would I rewrite this in matrix form?
1, 2, 5.
Yeah, 1, 2, 5.
-3, -1.
-3, 5. Okay, cool. And like I said, a computer would eat this process up. So that's why, of course, if you know how to make it into a matrix, you can plug that into the calculator. It'll chew it up and spit out the answer. All right, so now once we know how to do this, we're going to talk about how to put them in the calculator. And you guys are going to have to realize, of course, that that's just a way to check your answer. As always. All right, so if I start to solve this, what can I do to kill the x's here? Yeah, I can take row 1 and multiply by 3. So then I get 3x plus 6y equals 15. Yep. So you get 5y equals 20. Now, how would that look like in the matrix? So I'm going to go a little bit here and a little bit there. Let's just see, make sure that we get the same thing. I'm going to start this way. I'm going to see if you guys can handle this. I could rewrite the matrix. The whole reason the matrix exists is so that I don't have as much to write. So I could rewrite, if I could multiply this by 3, and I could put 3, 6, 10, and rewrite it. But why would I do that? Because the minute I do that, what's the only reason we wanted to multiply this by 3? To kill this dude. The minute he's dead, does the first one still have to have a 3 times it? No. It can go right back to the way it was. So I could rewrite this whole thing as 3, 6, 10, negative 3, negative 1, 5. But let me see if I can start with this idea, because I'm trying to get you to realize matrices cut down on the amount of work we have to do. Don't do that crap to yourself. Just put little 3, put next to it what it would be. 6, 10. Because you're going to take that first row right back to 1, 2, 5. 15. So then you tell yourself as you go along. So anything I can do with equations, I can also do with the rows, because the rows are equations, right? So I can add 2 rows together. Could I add 2 columns together? Hell no, because that's not like terms, right? I can't make that 1 plus 2 is 3 because that's x and y. So get that stuff down now, the very basics. So this is just taking the coefficients of this. I'm going to do the exact same stuff to that I would do to this. Just a lot less to write. So tell yourself what you're doing. I took 3 times row 1. I'm going to add it to row 2.
To make a new row 2.
Jesse, you freaked me out. I was about to ask you, where do you want to put the answer? I'm going to put it in row 2. This equation, would you agree with me that that equation is better than either one of these? Now, it's not better than both. I don't want to eliminate both of them because it still needs some idea what x does, right? But I can replace one of them with it. It's a much better equation. So that's exactly what we do. If I take 3 times row 1, add it to row 2, and put the answer in row 2, what do I get? 0, 5, 20. And the first row stays the same. So you really, until you get more comfortable with this, you only change 1 row at a time. I'll let you absorb it. Do you see how that's exactly the same situation, of course, as this captures here? Because once I figure out what y is, what am I going to do with it? Plug it back into one of these. So the matrix kind of keeps track of at least one of these guys. But let's take this a little further. What can I do to the last row here?
Divide by 5.
Yeah, so row 2 divided by 5, I get 1, 2, 5, 0, 1, 4. So of course this last row tells me what? Y equals 4. And the first row tells me the same damn thing it's told me since the beginning. But what could I do so that the first row tells me what x is?
Multiply row 2 by negative 2.
When you make zeros in a matrix, you're effectively killing that variable, and that's the most important thing you want to do. In order to kill other variables, you want to have a 1, so the second most important thing is to make 1s in your matrix. But the most important thing is to make zeros, because what's the most important thing to solve in this thing? Killing a freaking variable. Well, there's too many of them. Got to cut down on the population of variables. So here, how do I kill that 2 now?
Negative row, multiply row 2.
Yeah, so if I take negative twice row 2, and of course add it to row 1, and put the answer where?
Row 1.
2.
Why do I not want to put it in row 2? Because row 2 is already an answer. I don't want to screw with row 2, right? I want to keep that. So I want to put it into row 1. Because my answer is going to be better than row 1 is. Let me stop there for a second. So we're going a little further than we would here. Because we can. And if I had 3 of these bad boys, it'd be a lot easier just to keep going here. And make more zeros. So what do I put down here? 0.
Negative 2.
Negative 2.
Negative 8.
Negative 8. Decas. Right? Because that's what I told myself I'm going to do. Negative twice row 2. Beautiful. And what kicks me out about that 0 is it's not going to screw with my 1. So now I'm going to add these together. So I get
1,
1,
0,
0, negative 3, and 0, 1, 4. So what's my answers?
X
equals
Negative 3 and 4. Yeah, I love it. So you can just read it off right at the end. That is the answer. Big ass. All right, let me let that fully sink in. Yes, sir.
If we wanted to, could we show all the work by hand with the matrices rather than doing the elimination?
Oh my God, dude. So we're what did I mean by that? We're getting away from this entirely and moving to that. So right now I'm just showing you the connection between this and matrices. Once you understand the connection, we can totally move into matrices. Now to be honest, I did a 2x2 just so it's easier to look at, so there's not a lot of muss when you're first learning this stuff, right? I don't know if muss is a word, it sounds like it is. So it actually is easier to solve a 2x2 this way. That kind of like adds a little extra complexity you don't really need. But a 3x3, they're roughly equivalent. I'd say matrix is a little bit easier. And then the minute you go to 4x4, 5x5, the matrix just totally wins. Can you imagine 5 of these things with 5 variables? Trying to do that by hand? Whereas in a matrix, what am I just doing? I make a 0, make a 0, make a 0, make a 0. Okay, maybe. And that's why a computer program would eat it up. Find a 1, make a 0, find a 1, make a 0. It's just everywhere, yes.
For our like homework or tests or something, if we like started using one method, for example, we used like matrices and then jumped back into like substitution, would we get points marked down?
So the book shows that as a viable way to go. I'm stressing rather strongly that I want you to take it all the way to here. And this is what's called row-reduced echelon form. So you'll see in the calculator what you have to go to do this in your calculator is RREF, row-reduced echelon form. How important is that word? Just RREF is what's important. We're not there yet, by the way. I like that you're all getting ready. I want to do a 3x3 now. Here we go. So what would the goal be for really any matrix? When would I know I'm done? What would it look like?
There's only one, and then
There's a 1.
So if it's a 3x3, what would it look like?
1, 0, 0, and
Number,
0, 1, 0,
number.
0, 0, 1.
So that's my goal. That is my goal. This by itself is called the identity matrix. We're going to learn how to multiply matrices also. Not in the same section. But when I multiply any matrix by this matrix, any 3x3 matrix, it's going to stay exactly the same. It works like 1. Matrix multiplication is very different than regular multiplication, just to say the least. Yeah.
Now you said it's not gonna always look exactly like that, like the...
No, any 3x3, now it depends on how you solve it. You might have these ones out of order, but you basically want this. 4x4 would just have more ones in the diagonal, right? Cool. So this is like the upper triangle, the lower. You got all these weird little terminology things. And it really only becomes important if you ever have to get to linear algebra. So I know a couple of you guys have to do that. Linear is all about matrices. All about matrices. Yeah.
I know this is kind of off topic, but teachers' recommendations.
Oh, yeah, that's right. So remind me here in a bit. We'll stop a little early so I can come back. So, let's try a problem out. Let's do this one here. Yeah. Sorry. So let me just say this right now, just to get this out there, so somebody's still going to say this later. I'm going to teach the most by the textbook, you're not comfortable with this yet, way. The more comfortable you get, the more you can kind of make things flexible. So I highly suggest that you first get the first column to look this way, then you move to the second column, and then you move to the third. Because if you don't do that, you sometimes find a 0, and then you have to lose your 0, and that's the worst thing to do in a matrix. You want to make zeros and keep them. So if you do it, bam, 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 you will never lose one of your zeros. Okay? Maybe. So what would this thing look like as a matrix?
1, -1, 3, 4, 1, 2, -2, 10.
Okay. Appreciate that. It's like, you get the idea, Jeff. So it's not bad. It's just collect all the coefficients. Not a big deal. Now be careful. Take a little extra time at this step, because if you start doing it and you left the negative out, it's got one little negative mistake, the whole thing is never going to work. So take an extra check. All right. Measure twice, cut once. So you want to make sure that you got everything. Make sure you got this copied from the book correctly. Right. Okay. So, if I did not have a 1 here, I could move rows around, because does it really matter which order I put the equations down up here? So then one thing I could do with my rows is just move them around. I could switch row 1 with row 3. So if my 1 was here, I could just move it up there at some point, right? Because I know my goal is this guy. But I've got a 1 there. It's beautiful. So what could I do? Let me see if you guys are ready for like level 2 of making this quicker. Well, what do I do? How do I make some zeros? So I want to focus on column 1. You want to make zeros?
-3 times row 1.
Okay, good. So -3 row 1 plus
row 3.
Row 3.
Into row 3.
To row 3. I like it. Okay, let me see if you guys are cool with this. The less comfortable you are with what I'm about to do, the more matrices you can write for yourself. The more comfortable you get, the quicker these will be. So what's -3 times row 1? What am I going to put up here?
3, -9, -12.
Cool. So then if I go at -3 and 3, that's the reason we did that, right? 3 minus 1 is 2. I'll assume you know that. -9 plus 5. -4. And then -12 plus 14. 2. Now, let's see if we can handle this. How can I also kill this guy?
-1.
Yeah, I can do -1 times row 1 plus row 2 and put the answer in row 2. So what you do then is just cross these out or erase them, whatever you want to do. And right here underneath you put what that is. This is so much neater and so much more organized than it was when I was just free-floating XYZ crap. This is a lot more organized. So then, of course, this would be
-1, 2.
why 2? So this will be
Negative times a negative is
1.
a positive?
That's right.
Oh, yeah, 1. Duh.
And then -3, -4. Megan's trying to teach me. And then what do you get here?
0.
0.
3.
3.
-5.
-5.
And 6.
And 6. Kick ass. And then the first one stays the same. So if that was okay, cool. If that was not okay, break that up into a couple steps. If this is not okay at all, break it up into rewriting the entire matrix, replacing the first row with what 3 times it's going to be or whatever. Right? So the less comfortable you are, the more work you got to do. That's basically true for all of math.
Simplify the lowest one.
Cool, I like it. So this last one,
0, 1.
yeah. And of course, what do you think I would do? Maybe I'm going to try it right now. I would just put a 1, -2, and a 1. Let's rewrite. Just to be fair, so you guys can keep track a little easier. So we got 1, -1, 3, 4, 0, 3, -5, 6, and now we got 0, 1, -2, 1. So So now is my first column there?
Yeah.
Yes. So then I move to my second column. And what zeros? Where do I want to make zeros in the second column? Yeah, top and bottom. Kick ass. What kind of sucks about what's in the middle right now?
Just
3.
So I can just switch. Now watch. If that was a 2, why can't I use this guy?
Because there's already
Because that 1 is going to screw with my 0, and you never let that happen if you can help it. Some problems there might be a 0 somewhere in the beginning that you got to lose, but that's not your 0. You're okay with that. I don't want to lose those. That was hard to get there, damn it. I don't want to lose these things. So if that was a 2 instead of a 1, it's a 1. That's nice. I just have to switch these 2 rows, right? No problem. But if that was a 2, what could you do? So if I had like this,
divide the whole thing by 2.
no, see, you don't want to do that, do you?
Oh.
Can you imagine fractions in this thing? Like you had 7/8 there, and you got to multiply that 3, and add it to 8/11. Oh my God! Don't do that to yourself. You never have to. So watch what you could do. You could either multiply this by 2 and this by -3, and that would kill them, right? So you get a 0. Or even better, you subtract them because then you're going to get a
1.
See, so once you see what you're allowed to do, I'm allowed to subtract, add, multiply rows, move them around. If I want a 1, I can always make a 1 if I don't have it. By doing that kind of thing. Here, I'm okay. I got a 1 there, so I can switch row 2 and row 3. Hopefully some of you guys realize, I obviously, what did I just try to erase there? Somebody has spewed Ebola all over the board. I just tried to erase it in my hand. It's been nice knowing you guys. So, what was I trying to say here? So you guys hopefully realize I'm still showing more work than you really have to. Right? So if you're a little worried that it seems long, it's because I'm sort of showing more work than I really have to. But what can I do now? Who can I kill? So I can use that 1 to immediately kill that. Because remember, we're on row 2, we're in column 2. We want a 0 up here and a 0 down there. So I can make a 0 there easy. So now I just got to do row 2 plus row 1. Put the answer where? Row 1. That's where I want the 0 to show up, right? That one kicks ass because it's already what it's supposed to be. I don't have to put any little numbers next to it. So 0 and 1 that's crazy. 1 minus 1 is 0. Negative 2 plus 3. And 1 plus 4. How are we doing so far? Is it cool? So then the middle is going to stay. And then what can I do to kill that 3?
Divide by -3.
Yeah, -3 times row 2 plus row 3. And of course put the answer in
Row 3.
row 3. I got a little handout, by the way, I'm going to give out after this problem's done. It's got a whole example that shows you step by step what the hell I'm doing. So now, next to here, I'm going to put 0. For some reason, people put -3 there. 0, and then -9, 15, -18. So I'm going to add that to row 2.
Wait, why'd you?
Why did I say that?
Why'd you do row 3?
I don't know why I did that. Look at that sideways. Let's try this better. Let's do what I said I was going to do. -3 times row 2. So what I'm going to put here is 0.
-3.
6,
-3.
Okay, it's much better. Now things will actually die. It's good. So then I get 0 plus 0. 0. -3 and 3. 0. 6 minus 5.
1.
Kick ass. -3 and 6.
3.
Kick ass. So I already know that
X and Y.
Z is 3. Right? 0x plus 0y plus 1z is 3. So z is 3. That's what the last row says.
Yeah.
And what's really, really nice, of course, this will always happen, by the way, is you're going to divide this by whatever the hell it is, if it isn't already 1. So you'll always have a 1 here to kill these guys. All right, so you try to do the next 2 steps. So the last column, I want a 0 here and here. Do it. Finish that out. It's,
So, in order to solve these, is our whole goal just every time just to try and make an identity matrix?
exactly. Because then it guarantees you're left with what each variable represents.
I don't even want to ask, but I'm going to ask anyway. You
Did I
don't,
bring this?
on the test, will you care where our ones are as long as we only have one per?
You're fine. You don't have to have it exactly.
Okay.
Yeah. That's just one of these letters. You can have here. All right. Okay.
You got it, though? You got it. Thank you.
It's the same one I used
From last time?
this summer, yeah. Just added a few things to it.
Yeah, it's a little denser. I always got hung up on the ones. Always. Not for this question in particular, but when we're doing this, because I know you say ones aren't the big deal, just to refresh my memory, if it was like, say, 3006 or 22 or something, and then, 070 blah, 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 you still end up with numbers. At the end, you just
Divide each row to make a one, yeah.
Okay.
Yeah. Because that would be equivalent to 3x equals 22.
Yes.
And to solve that, you divide by 3. So in the matrix, you just divide the row by 3.
That's why you don't have to worry about ones.
Yeah, because at the end, you would recover them anyway. That's when they really have to be ones,
Okay.
is at the very end. And it's nice if they're ones in the middle, because 1 is the easiest thing to kill other things with.
Yes.
Cool. All right, let's see. How we doing here? All right, so what do I want to do to kill this -2 here? Yeah, twice row 3 plus row 2, and of course put the answer in row 2. So twice row 3 is easy enough. 0, 0, 2, 6. So then in the middle, I'm going to get 0, 1, 0, 7. Kick ass. And of course down here I'm going to leave this guy alone because he's where I want him to be. So I get rid of that. That stuff is unnecessary now.
Now you
Right?
multiply by
Erase it or
-1.
cross through it. And then how do I kill this guy?
By multiplying row 3 by -1.
Yeah, multiply by -1. So that means I'm going to do negative row 3 plus row 1 and put the answer, of course, in row 1.
Yeah.
Okay, cool. So then I get
1,
0,
0,
negative
0,
no,
and then
2.
2.
Oh, 2.
Yes. So something like 0, 0, 1, 3, I was thinking of that as like a laser. I'm doing this surgery and I want to kill the bad parts and leave the good parts alone, right? So my 0s leave the good parts alone and the 1 is the laser killing these guys. It's a laser.
Yeah.
Can it be a lightsaber?
Sorry. So I imagine you guys, my math teacher thinks that this is a laser. Alright. This is what I put up with. Okay. So, that's that. You got the little handout. Next thing I want to talk about real quick.
Nothing.
So we got what they want from here.
Did you get math 180 yet?
Oh. Real quick before we do that. Last thing before we do that. I had a certain place I wanted to get to and I'm not going to do it, but I wanted to at least get close.
No multiplying.
No, multiply, that's going to take a little bit of time. What's your gut instinct say about that?
Add each. Add 2 to 3, add 7 to 1.
So the step that we take, this completely makes sense where it came from. But matrices can live on their own. They are their own constructs. Like the number 7 doesn't have to be a part of an equation to have any meaning. 7 can exist on its own. So a matrix could be a part of an equation, or it could just be its own thing. So the minute we learned numbers, you very soon after that learned how to subtract them, add them, multiply them. There's no such thing as matrix division. But yeah, your gut instinct would say
5.
2. And your gut instinct would be right. I love it, of course. It makes sense. It's sort of like adding a couple of different equations together. And then they're like terms. These are my x's, these are my x's. That kind of thing. So, but what did your gut say about this? Let's see how far you can trust your gut here.
Add a 0 column? I would, no?
0 is a number in its own right. What is after the second column? What is there?
1.
There is the void, right? There's nothing. What color would the universe be if there was nothing? Think about that time. So I can't. These are not good. These do not have the same dimension. Right? So there's like an extra level of like terms with matrices. So what dimensions does this have? How many rows?
2.
How many columns?
2.
This is a 2 by 2, like I was saying earlier. This is also 2 by 2, but this is a 2. Careful.
2 by
2 rows, 3 columns. Good. So the first one's rows, second one's columns.
And you can't add those together?
Because they're not the same dimension. You cannot add them together. You could multiply them together, which is interesting.
We're not there yet, though.
We're not doing that yet, because multiplication of matrices takes a bit of getting used to. Now, where do you think matrices happen in everyday life?
Computers.
And what part of computers normally? A lot of them, but the most obvious one would be
Calculating.
A1 is 7, B2 is 8. And it sounds like I'm playing Battleship. It's Excel spreadsheets. I mean, those are all freaking matrices. So it's got a lot of matrix algebra built into it.
You never did show us doing it in a calculator.
So I'll show you tomorrow. Tomorrow, first thing I'll show you how to do it in the calculator. So you guys don't cry over the weekend. I don't know why I let us out so early.